All right, thanks for the introduction. So I'm excited today to tell you about practical constructions of graphs which can be used to construct optimally side-channel resistant memory hard functions. So this is joint work with Joel Alwyn and Ben Harsha, my student at Purdue. Okay. All right, so as the motivation for the problem, consider the challenge of password storage, right? So an attacker breaks into the authentication server, they steal the salt and the password hash, and now they can mount a fully automated offline attack to try to crack the user's password. So offline attacks are a common problem. Password breaches at major companies have affected millions of users. Actually, this slide's out of date. It's not millions of users, it's billions of users accounts after the latest Yahoo breach. Right, so offline attacks are an increasingly dangerous problem. So password cracking hardware continues to improve. So for example, here's the Antminer S9. It's a Bitcoin mining machine, and it can compute the SHA-256 hash function 14 trillion times per second. And it only costs about $2,400 on Amazon. On the other hand, users still struggle to select strong passwords. So we have fairly predictable password distribution. So the basic goal of memory hard functions is, can we increase guessing costs for the attacker, right? We want to make a hash function that's prohibitively expensive for the attacker to try millions or billions of guesses. So the first attempt here would be to just take your hash function and iterate it. So for example, password-based key derivation function, this is the function that was used by LastPass when they were breached. They were iterating SHA-256 100,000 times. Well, if you just do a dollar estimation, we would estimate that this is about $1 per billion password guesses. By contrast, 70 million password guesses per user is sufficient to crack vast majority of user passwords. So the real challenge here is that on the one hand, the cost to compute a cryptographic hash function like SHA-256 is steadily decreasing as hardware improves. On the other hand, user patience is not improving, right? So a user is not willing to tolerate longer and longer authentication delays, which really bounds the number of times that we can iterate a hash function. So the goal here is to design a moderately expensive hash function. And the hash function should be fast on a standard personal computer. And it should also be prohibitively expensive for an attacker to compute millions or billions of times on customized hardware. Right, so this is where memory hard functions come into play. So the intuition of a memory hard function is you want a hashing function whose computation costs are somehow dominated by memory cost, right? So instead of forcing the attacker to just use a small chip on his circuit to compute this hash function, we're going to force the attacker to allocate a large amount of memory throughout the duration of computation. So basically, right, the goal is we want to force the attacker to allocate, let's say, 1 gigabyte, 4 gigabytes of RAM, just to compute this function one time. So scrypt, of course, is an example of a memory hard function. The downside to scrypt is that the memory access pattern induced by running this algorithm is data dependent, which means that this function is potentially vulnerable to side channel attackers. So in this talk, we'll focus primarily on data independent memory hard functions, which are memory hard functions whose access pattern does not depend on the input. And in particular, if the memory access pattern doesn't depend on the input, then there's no side channel attack through cache timing. So what is a data independent memory hard function? Well, formally, a data independent memory hard function is given by a directed acyclic graph G and an underlying compression function H. So to compute this function, we start off with the first node, and the label of this node is the hash of the password in the salt, the input. The label of an intermediate node, take L3, is just the hash of its parents in this graph. So you take label of, in this case, hash of node 3 is label 2, append label 1, and hash it together, and that gives you label 3. And finally, the output of the function is just the label of the final node in this chain. So to evaluate an MHF, it's helpful to use the language of graph pebbling. So here, graph pebbling is just a game in which you can place pebbles on each node. Placing a pebble on a node means that you're computing that particular value. Of course, there are some constraints, right? So you can only compute a new label if you happen to have all of the initial dependent values in memory already, right? So you can place a new label on a new pebble on the graph if and only if during the previous step you had pebbles on all of the parents of that node. And of course, you have to eventually finish. So in your pebbling, you have to eventually place a pebble on the final node and compute your output. So here's just a simple example of graph pebbling. So we start off with no pebbles on the graph. Then we can place a pebble on node 2, which means that we store label 1 in memory. Place a pebble on node 2, place a pebble on node 3 now. Simultaneously, we could discard pebbles on node 1 and 2 to save space. Then we can place a pebble on node 4, node 5, and now we're done. So how do we measure the cost of a pebbling algorithm or an evaluation algorithm for this MHF? Now the first approach, which is kind of natural, is space-time complexity. Right, so space is kind of the maximum number of pebbles on the graph at any point in time, multiplied by the total running time of this pebbling. So this is a nice metric, and there's a rich theory examining space-time complexity, but I claim that it's not appropriate for password hashing. And the real problem here is that for parallel computation, amortized space-time complexity can scale badly in the number of evaluations of the function. Here's a simple example. So suppose that we have a pebbling which initially uses a lot of space, and then you can discard most of the pebbles for the remainder of your computation. Right? In this case, an attacker that wants to compute this function 3 times can just overlay computations. And in this case, you can do 3 times the amount of work without significantly increasing space-time complexity. Right? So in general, there's counterexamples where the space-time complexity to compute this function or to pebble this graph really scales badly with the number of instances being evaluated. And of course, the attacker wants to try, compute this function on millions or billions of password guesses. So we want cost to increase linearly with the number of guesses that the attacker tries. So instead, we use a metric called amortized area time complexity. Instead of looking at space-time complexity, which is the bounding box around this curve, we're looking at the area under this curve. So that's the sum of the PIs. So sum over all time steps of number of pebbles on the graph at that particular time step. We also add this second factor here, which is r times the number of new pebbles placed at each step. I should mention that in an asymptotic sense, this is the smaller term, but for practical purposes, we want to include it to make a fair comparison with other IMHF candidates. The nice thing about amortized area time complexity is that it actually does scale linearly with the number of password guesses. So if you want to check m guesses, the cost is m times the cost of checking 1 guess, which is what we would like. So in our previous pebbling, here's an example of amortized area time complexity. So if we just sum the number of pebbles on the graph at each step, trust me here, the total is 7. Plus we have to place a pebble on each node, so that's cost 5 times r. So what's the goal then for a memory hard function? Right. So the goal is to find a graph G on n nodes with several properties. First, we want the graph to have constant in degree, and that's because in practice the time to pebble the graph is actually proportional to n times in degree minus 1. Right. So if you boost the in degree, then really you're kind of blowing up the running time to actually compute this function in practice. We also want the graph to have the property that the amortized area time complexity to pebble this graph is at least n squared divided by tau for hopefully some small value tau. The reason here is because we're trying to maximize the cost for a fixed running time n. Remember, n is running time, users are impatient, so we want to make this function as expensive as possible with minimal n. Right. So the paper is about constructing depth-robust graphs. So it might seem strange. How is this related to memory hard functions or password hashing? The connection is here. Depth robustness, it turns out, is the key property to building an MHF with optimal amortized area time complexity. So there's a collection of papers at Crypto 2016 and at Eurocrypt. Eurocrypt 2017, showing that depth robust graphs are both necessary and sufficient to construct a secure data independent memory hard function. And there are other applications to depth robust graphs like proofs of sequential work, but I'm going to focus on memory hard functions for this talk. Okay, so what is depth robustness, our key property? So we say that a DAG G is ED reducible if there exists a small subset S of at most E nodes, such that removing those nodes from the graph reduces the length of the longest path in the graph to D, right? Otherwise, if a graph is not ED reducible, we say that it's ED depth robust. So here's an example of a 1-2 reducible graph. That means we can delete one node, and the length of the longest path in the remaining graph should be at most 2. And hopefully it's obvious, delete node 3, and proof by picture, any remaining path has length at most 2. So why is depth robustness important? Crypto 2016 result shows that if G is not ED depth robust, then there exists an attack, reducing the amortized area time complexity. In particular, any graph with constant n degree has amortized area time cost at most n squared log n over log n. So it seems that you lose, you have to lose this log n factor in any construction. In fact, what we found is that for practical IMHF candidates, including Argon 2, the winner of the password hashing competition, you actually get much stronger attacks in practice. Okay, so depth robustness is necessary to design a secure IMHF. It turns out it's also sufficient. So this is a Eurocrypt 2017 result. Basically, if your graph is ED depth robust, then your amortized area time complexity is at least E times D. So the implication here is that there actually exists a constant n degree graph with amortized area time complexity at least n squared over log n. So this is nice. In particular, you can't hope to do much better in an asymptotic sense. But I want to highlight this word here. There exists. So this result was an existential result. It uses combinatorial construction of Erdos, Graham, and Semiretti back in the 1970s. But this particular construction was not practical. It's not something you can actually build or deploy. So this motivates our results. So we give a practical construction of a highly depth robust graph. In particular, the graph is n over log n depth robust, which means if you delete any subset of n over log n nodes, there's still a linear size path in the remaining graph. What do I mean by practical here? Well, I mean it in an empirical sense. I mean it in the sense that you can actually change or modify the Argon 2 source code, tweak it to use our new edge distribution, and you get no adverse performance impacts. So that's what I mean by practical. So what does this new construction look like? Well, we start off with a hash chain, nodes 1 through node n. And then for each I, we pick a random predecessor. And the only real modification of Argon 2 is we're just tweaking the distribution of this predecessor edge. Right, so what does this distribution look like? Well, to sample the predecessor, we start by partitioning the previous nodes into log I buckets. So we'll start with bucket 1. Bucket 2 will have twice the size. Bucket 3 will have double the size of bucket 2, et cetera, et cetera. So we end up with log n buckets. And then we're going to select one of these buckets uniformly at random. And then we're going to pick Ri uniformly at random from the selected bucket. So it's actually a pretty straightforward algorithm to sample predecessor edges. Now I should note here that if you sample this predecessor uniformly at random, you're basically going to ignore buckets like B1, B2, and B3. Because if you pick your predecessor uniformly at random, it's highly unlikely that you're going to pick something close to node I. Our distribution, is biasing a little bit more towards picking closer edges. So the analysis of this graph, we show that it's first highly depth robust, which in light of recent Eurocrypt results implies that it has maximal amortized area time complexity. So how do we actually prove this? I'll just give you a hint, brief hint of the proof. So we start off with the original graph, and then we construct a metagraph. So we kind of chunk each, group the nodes into chunks of size, log n, and then we design a new graph where two meta nodes are connected, if and only if they're if and only if there was an edge between those two chunks of nodes in the original graph. And what we show is that this metagraph, it has n over log n nodes, n degree log n, and it's maximally depth robust, right? So it only has n over log n nodes, but to really reduce the depth of this graph, you have to remove n over log n meta nodes from this graph. So how do we show that this metagraph is depth robust? Well, there's two key ideas which are kind of inspired by the Erdos-Graham-Semiretti proof from the 70s. So we introduced the notion of a local expander node. And we say that a node is a local expander if for every interval r, you can take the node r, and then you can take two intervals, consecutive intervals of size r, centered around node r. And these two intervals, if we just view them as a bipartite graph, they should be connected by a bipartite expander. Similarly, if we start these intervals at node I and then take the next sequence of R nodes, we should also have the property that these two intervals are connected by a bipartite expander. So that's what it means for a node V to be a local expander. Then we also use the notion of a SeeGo good node. So given a set of nodes that we're deleting, we can say that a node V is C good with respect to this set S. If again, for every interval centered around V, the fraction of deleted nodes in the set S is not too large. So here, if we look at this node, there's at most C times R deleted nodes in this interval. So what we can show is informally, if you don't delete too many nodes, then most of the nodes in this graph are C good with respect to the set S. And what you can also prove is that if two nodes V and W are both C good and local expanders, then there must be a path between nodes V and nodes W in this graph G minus S. So in particular, most of the graphs are C good, most of the nodes in the graph are local expanders. So if we don't delete too many nodes, then there's a path running through all C good local expander nodes, and it turns out that this is almost all nodes in the graph. Okay, right. So the corollary then is that this metagraph is maximally depth robust, and that implies that the original graph is also maximally depth robust. Here we gain a log factor back in the length of the path, but we lose that log n factor in the size of the set of nodes that we're removing. Okay. So in particular, this implies that the amortized area time complexity of our construction scales with n squared over log n, which is, in an asymptotic sense, the best you can hope for. Now, I want to add a disclaimer here in that the constants in the provable lower bound are still small. So there's still work to be done to improve the constants in this analysis. I would conjecture that with a lot of work, one could improve the constants, but I don't want to suggest that all work in the space is done. This big O notation is hiding some ugly constants. Okay, so if the constants in the lower bound are ugly, we might wonder, in practice, does DR sample actually give us anything interesting? And the answer is yes. So we conducted an empirical security analysis in which we took all of the known attacks and kind of threw them against our construction. So we also threw these attacks against other constructions like Argon 2. We considered an earlier version of Argon 2, which we call Argon 2IA. And we just threw all of these attacks against each construction. And here we plot attack quality versus the running time parameter. The running time parameter here is plotted in log scale. So in particular, attack quality is just the ratio. It's the cost of the honest evaluation algorithm divided by the attacker's amortized cost, right? So plots towards the bottom here are more secure. And in particular, DR sample is this green plot at the very bottom. Argon 2I A and B are these red and blue curves at the top here. So our construction really yields concrete improvement. I should mention also that this dotted red line is the previous best attack on Argon 2I or Argon 2B. So we also get just improved attacks against both classes of graphs in comparison to previous state-of-the-art work. So we implemented our construction, basically just modified the Argon 2 source code to use this new depth robust edge distribution. So to measure performance, we ran it with n equals 2 to the 20 blocks, so that's a gigabyte of memory, and found that the running time is pretty comparable. In fact, DR sample was epsilon faster than Argon 2I. So in summary, there seems to be no adverse performance impacts by making these modifications. If you're interested, all this source code is publicly available on GitHub. Okay, so stepping back, I want to revisit the issue of data-independent versus data-dependent memory hard functions. So recall that data-independent memory hard functions have this advantage that they resist side channel attacks, but the disadvantage is that the amortized area time cost is at most n squared over log n. That's kind of the best we can hope for. Now for data-dependent memory hard functions, this upper bound doesn't hold. So that's an advantage, but they're also potentially vulnerable to side channel attacks. So the current trend is to move to a hybrid mode. So Argon 2 ID, which is in response to some of these attacks, now the current recommended mode for password hashing in Argon 2. Basically what it does, it runs in data-independent mode for n over 2 steps, and then you switch to data-dependent mode for n over 2 steps. So because you run in data-dependent mode, this means that you can defeat attacks on data-independent constructions. But of course, in the event of a side channel attack, security reduces to security of the data-independent mode, right? So in the event of a side channel attack, security reduces down to amortized area time cost. Scaling is like n to the 1.767, I think, is the best current attack on Argon 2I. So this is an improvement over scrypt, but we can hope to do better with DR sample. In particular, we could use a hybrid mode with DR sample, and in this case, side channel attacks can reduce costs, but not by too much. So the cost reduction is just from n squared to n squared over log n. So in the event of a side channel attack, you potentially lose a log n factor in the cost, but not much more. So some new results. We've also managed to prove that DR sample is capacity hard following an upcoming TCC paper of Ling Ren and Srini Devadas. On the downside, we've found now tight attacks against DR sample. So in particular, there's an attack which actually achieves amortized area time cost at most n squared over log n. And this is actually just the greedy pebbling attack given by Bonnet et al., I believe, at AsiaCrypt. So on the positive side, this evaluation algorithm is actually sequential and could be run by the honest party. which could be good for the goal of honest computing, but it falls short of our goal of maximizing cost for a fixed running time. So we might hope that for practical values of n, n smaller than 2 to the 24, that really we have no attack on amortized area time complexity. So future work, we want to really balance resistance to the AB16 attacks and this Bonet-Gibbs et al. Attack. So that's one practical challenge to address in future work. So in summary, we give the first practical construction of highly depth robust graphs. It's just a simple modification to Argon 2, and we get an IMHF with optimal asymptotic security guarantees. We get a hybrid mode with optimal side channel resistance, and we actually conjecture that it will yield tighter resistance to space-time trade-off attacks as well. So of course, more research is needed to understand the constant factors in these security bounds. So that's one of the big open challenges that I hope people will start to work on. So thank you for listening. I can take questions, and I also have a puzzle here, and I'll pay people $20 to the first person to solve it. Well, it runs in data independent mode first, and then switches to data dependent mode. So if there's a side channel attack, basically security compresses to that of the data independent mode, right? So even in the event of a side channel attack, you still get this n squared over log n security. Yeah.
From what I understand, the construction is sampling randomly, right? A DAG that's going to be with high probability a depth robust graph.
Yeah.
So like all the previous works about constructing depth robust graphs and like using explicit constructions of expanders, like the whole point there was that the expanders, to get explicit expanders, you needed to do these complicated zigzag constructions. But
right.
If you just want an expander graph, it's well known that you can randomly sample a graph and with high probability will have good expansion properties. So how can you compare this to a construction where you're just using the classical constructions for depth robust graphs, but the expanders, instead of using like the zigzag product constructions, you just use randomly sampled graphs that have good expansion?
Right. So yeah, in some ways, our construction could be viewed as kind of an adaptation of classical constructions like Erdos-Graham Semiretti, but replace the explicit expander graphs with a randomized construction. The new analysis really is actually, if you do the randomized construction, it doesn't actually hold that every node is a local expander, which is one of the challenges I kind of glossed over in the slides.
Right.
So this is one of the technical special cases that you have to hold. But at an intuitive level, yes, you could view it as kind of taking a classical construction and replacing expander graph with a randomized bipartite or randomized expander.
Thanks. Okay.